Okay, let's just go through one quick example of an RLC circuit. In this series RLC circuit shown, we got R equals 300 ohms, we got L equals zero point 0.9 henries, the capacitance is 2 microfarads, and the angular frequency is 1000 rads per second. We can work out the inductive reactance because we know that's WL, so that comes to 900 ohms if we plug those values in. And the capacitive reactance comes to 1 over WC, and that comes to 500 ohms. So you can see already from this that the voltage will drop mostly across the inductor because that's got a higher reactance than the capacitance. The reactance capital X, which we said was XL minus XC of the circuit, is therefore 400 ohms. So that's the total reactance of the circuit. And the impedance Z is R squared plus the reactance squared, and that comes to 500 ohms. So we've got the total impedance of the circuit. If the circuit is connected across an AC source of voltage amplitude 50 volts, then the current amplitude we can work out by using the maximum and the impedance, and that comes to 0.1 amps, so 50 volts divided by 500 ohms. So that gives us the maximum amplitude of the current. The phase angle, phi, which is the angle between the current and the source voltage, that is equal to, as we said before, arctan of x over r, and we've got the x, we've got the r, that comes to 53 degrees. So we've got all the information we need now. The voltage amplitude across the resistor then is VR, I, we've got I, R, that's 30 volts. The voltage amplitude across the conductor and capacitor are I again times XL, that's 90 volts. And across the capacitor is 50 volts, yeah, so you can see that more voltage dropped across the inductor because we can see that the inductor gave us a larger reactance value, so more voltage dropped across it. Less voltage dropped across the capacitor, and you can see here that the voltage is leading the current here. We can resolve these phasors, and we can see that the voltage is leading this current here by this angle phi. When we know the angle phi, it's worked out as 53 degrees. So then it's very easy to just write down the equation because we know that V is WT. Well, we drop that down to find the instantaneous value of V, was lowercase v. That's simply the magnitude of V times cosine WT, which I've written down here. So the instantaneous value of V is the magnitude of the voltage, the amplitude, the maximum amplitude, times cosine WT. We can see here that the current is lagging the voltage by this 53 degrees. So then it's very easy. We can just write down the instantaneous current. So we drop that down for the instantaneous current, and we get capital I cosine WT minus 53 degrees. So you can see that you'd have to go up WT up to here to get to this one. We're after this one, so then you'd have to subtract. If we treat it as that function cosine WT, to get in terms of I, you've got to subtract that angle there. So it's WT minus that angle. So that's why we can write down the instantaneous current in terms of this cosine function here. So that's really a quick example and show you how you can work out the equation and how you actually calculate it using phasors. Yeah. So with phasors we can work out the voltage drop across all of these components, and it brings up some interesting things. For example, the inductor here is dropping the most voltage, and the capacitor is dropping lesser voltage. The other interesting thing, of course, is the source itself is 50 volts, but you can see here that the voltage drop across the inductor is 90 volts. So it looks like it's higher than the source. And when you add the phasors up, you still get the source voltage 50 volts. So that's a good example of how it works, and it's interesting to see that the voltages are different once you get the answers.